This video is going to cover the first half of Chapter 3, Descriptive Statistics and the Normal Distribution. There will be a second video in this module covering the second half of Chapter 3. Our objectives are to illustrate types of data and associated measurement scales, calculate descriptive statistics on data, and graph and depict data. The first thing we're going to discuss are scales of measurement. All levels of measurement represent a taxonomy. If you recall from Chapter 1, a taxonomy is a hierarchy where the previous steps need to be accomplished before the next steps. When we're looking at measurements, taking a measurement often results in assigning a number to represent the measurement. For instance, height, weight, time. However, not all of the numbers are the same. Some types of numbers can be added and subtracted, and the results are meaningful. Other types of numbers have little or no meaning. There are several different scales of measurement that we can use. The first one we're going to talk about is nominal measurements. Nominal measurements are categorical in nature. There's no notation of order, magnitude, or size. Everyone within the group is assumed to possess the same degree of the trait that determines their group. So what is a category? Some examples are football positions, gender, or major. Again, for all of these, there's no difference in magnitude. It's just a categorical differentiation. The second scale of measurement is ordinal. This is also categorical in nature. However, the numbers are ranked in order, but the difference between the ranked positions is not comparable. Some examples are year in school, or income, military rank, or grade. If we think about year in school, we do first grade, then second grade, then third grade. So there's a difference between the grades, but they're not comparable. It's just the order in which they occur. Same thing with placements in a race. The person that places in first versus second versus third might all have different times, but what we're looking at is the order in which they completed the race. Another scale of measurement is continuous. This can further be broken down to interval or ratios. So continuous, numbers are said to be continuous in nature, and if they can be added, subtracted, multiplied, or divided, and the results have meaning. They have a distinctive place on a number line, and again, can be interval or ratio, and we'll break those down on the next slide. For interval data or measurements, an equal or common unit of measurement is used, and the 0 point is arbitrarily chosen. The value of 0 just represents a point on the number line, not the absence of that trait. An example of this is temperature. For example, 0 degrees Celsius does not indicate the absence of heat, but rather the temperature in which water freezes. The same with temperature in Fahrenheit. In Fahrenheit, water freezes at 32 degrees, but then we have 0, and we also have negative temperatures. So the 0 is just a point on the number line. It doesn't mean we don't have temperature. Other examples of this would be an SAT score, an IQ test, or shoe size. So the numbers matter and are an equal or common unit of measurement, but the 0 is arbitrary. In contrast, we have ratio data, which is still a continuous measurement, but there is an absolute or true 0 point, indicating the absence of that trait. For example, if we think about weight, 0 grams means there are none. Okay, we can't have negative grams of weight. Or if a person is 6 feet tall and another is 3 feet tall, the first person is twice as tall as the second, and a height of 0 would be the absence of height. So other things are age or weight. Only interval and ratio data can be subject to mathematical operations. Again, only interval and ratio data can have mathematical operations applied to it. That is not true for categorical or ordinal data. So we're going to talk about which scale of measurement is most appropriate. I want you to answer for yourself. So if we're talking about height, which is most appropriate? It's ratio data. If we're talking about a football jersey number, nominal, gender, nominal, placement in a race, ordinal, and temperature, interval. Now we're going to talk about some of the math terms. There is going to be some math in this class. We have our summation notation. So a capital N means the number of cases. A lowercase n is the nth or last observation, as we'll see down a little bit. An x is any observed variable that you might measure. Then we have the Greek symbol sigma, which is the sum of all values. So when we look below, we have sigma x, which equals the sum of all of the x values is equal to x1 plus x2, and so on till x of the nth, or the last observed. We always want to do everything inside the parentheses before moving outside of them. So if we're looking at the last bullet point, the first is the sum of x to the quantity squared. So we would add all of the x's and then square the sum. That is not equal to the sum of x squared, which is the second part of the expression in the last bullet point. The second would be the sum of the squared x. So you would square each of the x's and then add them all together. Here we are going to practice some of that math. You've got two equations. I'd like you to pause the video and calculate these for yourself. The answers will be on the next slide with a breakdown of how to get there. This is the breakdown of the math from the previous slide. So the answer to number 1 is 99.5, and the answer to number 2 is 295. When we're reporting data, we want to know how your performance compares with others. So we've developed frequency distributions of the test results. A frequency distribution is a method of organizing data that involves noting how often each of the various scores occur. This is figure 3.1 from your textbook. It's an example of a frequency distribution. This specific distribution looked at VO2 max for 65 different students. If we look in the left-hand column of the VO2 max where it says valid, we see scores ranging from 41 to 55. Those were the different values students got for VO2 max. If we look in the next column, it says frequency. So what that means is one individual got a VO2 max of 41. 3 individuals got a VO2 max of 43. If we look farther down, 11 individuals got a VO2 max score of 48. And if we proceed to the bottom, 1 individual got a VO2 max score of 55. that last row says total. So if we added up all of the different frequencies, we would get 65, which is our N, or our number of subjects. We can also see that in the top part of the chart where it says N valid 65. This means that each student is only being represented once, and it correlates to their score. We can also look at percentiles. So we can do this from a frequency distribution. A percentile is a score or value for a specified percentage of cases in a distribution of scores. So that means it's our frequency number divided by total people, or our capital N. Our 50th percentile, or P subscore 50, is the score that divides the distribution in half and is also known as the median. Quartiles and deciles are commonly used in percentiles. If we look at the same table from the previous slide for VO2 max, we can determine the percent for each of the individual scores. So if we look at the score of 41, we know it has a frequency of 1. So 1 out of the total number of people, which was 65, gives us 1.5%. So 1.5% of the data scored a 41 for VO2 max. If we look down at 50, the score of 50, we see that 7 people had a score of 50. So 7 divided by our big N, which is 65, gives us 10.8%. Okay, so that's how we determine our percent. And then if we look at the top where it says percentiles, our 50th percentile, or our median, is 48. We also have percentile ranks, or PRs. These represent the percent of observations at or below a given score. The percentile rank is how you compare to those at or below you. In the VO2 max table presented in the corner here, that we've also seen earlier, this is displayed as cumulative percentage. How they calculate cumulative percentage is taking the percentage and then adding it to the next one. So, for example, our frequency for our percentage for a score of 41 is 1.5. If we look at 43, our percent is 4.6. So 1.5 plus 4.6 is approximately 6.2. Due to rounding errors, there's a slight variation. So then they took 6.2 plus 4.6 to get the 10.8, and so on. For this example, a percentile rank of 90 means that you have a VO2 max higher than 90% of the people who were tested. Okay, so if we look at the cumulative percent, 90.8 is equivalent with a score of 52. I'm sorry, with 52. So if you scored a 52, you scored higher than 90% of the people. Another example, if we look at this table, if you scored a 46, your percentile rank is 26.2. That means that 73.8% of people scored higher than you. Percentile rank is a norm referenced or relative comparison. I would now like you to pause and practice making a table. This table should have a frequency distribution, percent, and cumulative percent for the following data set. Do this by hand, and the answers will be on the next slide. I know that I've asked you to do some math already. We're going to switch gears a little bit to things that I think most of you are a little bit more familiar with. We're going to talk about central tendency. This is a single score that best represents all the scores. The ways that that can be displayed is our mean, our median, or our mode. We'll talk a little bit about each of these on the next slide and the strengths and weaknesses of them. The first central tendency measure is mean. So the mean is the arithmetic average. It's the sum of the scores divided by the number of scores. It's the most stable measure of central tendency, but it may not be representative of skewed data sets. For example, if we have a data point that is outside of everything else, it can skew the set. It's affected by numerical values of every score in the data set. How the mean equation is noted is at the bottom. So the capital M stands for mean. Then we have our sigma, which means sum of. Then we have our x. The x is each observation or each data point. And then divided by n, which is our number of observations. The median is also a measure of central tendency. This is our middle point. It's our 50th percentile. It's the most typical score in the distribution. It means that half the scores are higher and half the scores are lower. It's the point that divides the distribution of scores exactly in half. To obtain the median, the order of the scores is from high to low, and then you find the middle point. This works best for skewed data sets because each n, or each observation, is just looked at and we're looking for the middle one. So that outlier or skewed set doesn't pull the score like it does in the mean. Our third central tendency measure is the mode. The mode is the most frequently observed score, but it's the most unstable measure of central tendency. There can also be more than one mode if two or more values are equal. The last topic that we're going to talk about in this part of the video is skewness. So skewness is the statistical term for the shape or symmetry of a distribution. A distribution with little skewness has values close to 0. A positively skewed distribution has a tail towards the positive end or right, and a negatively skewed distribution has a tail towards the negative end or the left. And I'll show you examples on the next slide. This shows the differences between a normal, positively skewed and a negatively skewed distribution. If we look at the middle one, we can see it forms this perfect bell curve. That means the mean, median, and mode are all the same number, and it's symmetrical. If we look at the graph on the left, the negatively skewed, we see that there's kind of this tail going to the left. If we look at where the median is, we can see, again, the median is that middle number. It's to the left of kind of the peak, and then our mean is even farther left. That means that we have some scores that are outside of that normal distribution that are pulling our measurements of central tendency to the left. On the contrast, on the positively skewed, we see that the mean is closer to the tail on the right. Same with the median. And then our mode, again, is that middle or most oftenly occurring score. So positive, tail to the left, negative distribution, tail to the right, normal, kind of in the middle. The last concept we're going to talk about is kurtosis, which is the peakedness of the curve. We have a mesokurtic, which is a normal curve, which is the top photo, a flatter curve, which is a platykurtic, or a lower peak, and then a leptokurtic or steeper curve or a higher peak. We're not going to spend a lot of time going over this, but it's something I wanted you to be familiar with. The following slides are some review questions for this video.